Hello and welcome to Guessing the Specialist Exam Part 5. Last year I guessed it, but this year my past students are doing it. They've got a tutoring company. You've probably already heard of it, but maybe you haven't clicked the link. I know 300 of you signed up the other day, but that's less than the people watching this video. So if you haven't signed up, do it now. Let's do it. First question. I have a feeling we're into some simpler questions here at the moment. So a bit of a break from some of the harder ones. Have a try. Alright, so we've got a complex number here, and we're going to raise it to the power of 4. So very straightforward. When you want to raise a complex number to the power of anything, you've got two things to do. One, you've got to increase the magnitude of it by raising that to the power of 4. And the other thing you need to do is rotate the complex number by multiplying it by 4. So, easy to make a silly mistake here in the specialist exam. 2 times 2 times 2 times 2. 2, 4, 8, 16. Sis. 4 times 3 is 12. 12 pi on 5. Now, you can see 12 pi on 5 sitting up there, but that is not going to be the answer to that question. Why is 16 sis 12 pi on 5 not the answer? Because that is not a simplified answer, and we want a simplified answer here. So, 12 pi on 5, that angle is more than a full rotation. So, I can come up with an equivalent answer by doing 12 pi on 5 minus 1 rotation, minus 2 pi. Now, if I'm subtracting 2 pi from 12 pi on 5, it's going to be easier to write 2 pi as 10 pi on 5. So, 16 sis 12 pi on 5 minus 10 pi on 5 is 2 pi on 5. And I can see my answer up there. The answer is C. Alright, big celebration, and on to the next question. Alright, have a try yourself, and then I'm going to jump in. So it is a partial fractions question. So we've got 3 over, what is it? X squared minus x minus 2. So first step here, you really need to factorize this. So it's going to be 3 over x, and what do I need? Like probably negative 2 plus 1. That feels right. Okay. Then we can split this up, and we can say 3 over x minus 2 times x plus 1 is equal to a over x minus 2 plus b over x plus 1. Right, simple, straightforward. Now, we can add those two fractions together, and the easiest way to do that is to multiply this by x plus 1, a bracket x plus 1, and this by x plus 1 as well, and multiply this by x minus 2. Now, when we do that, we're multiplying x minus 2 by x plus 1 as well, and we're multiplying x plus 1 by x minus 2, making the denominators the same, x minus 2 times x plus 1. Okay, so what have we got? We've got the fact that a x plus 1 plus b x minus 2 is equal to 3 over x minus 2 x plus 1. Okay. Something people sort of, when they're doing partial fractions, they forget that they're doing it. Now that we know that 3 over this is equal to this over this, we can kind of just ignore that, right? We can just say 3 is equal to a x plus 1 plus b x minus 2. Easy done. Now, you just need to sub in some convenient values. One convenient value to make b disappear, and one convenient value to make a disappear. So, what convenient x value will make b disappear? If I make x equal to 2, let x equal 2, we'll get 3 equals a, 2 plus 1 is 3, plus b, 2 minus 2, which is 0. 2 minus 2 is 0. 0 times b is 0. Done. So, 3 is equal to 3a. 3 is equal to 3a, and a is equal to 1. So we know that this a value is equal to 1. Alright, so we're halfway there. It looks like in our solutions we have a 1 over x minus 2 here and we have a 1 over x minus 2 here. So it looks like the answer is going to be A or C. We can do this same thing again, the thing that is in pink. We can do it again, but with a convenient value that makes A disappear. Now, it turns out that convenient value is -1. So I've subbed in -1 here and here. Okay, so that means that 3 is equal to, that is 0, and this is -3b, which means that b is equal to -1. So, putting all of this together, we have 1 over x minus 2 plus -1 over x plus 1. Now, none of our solutions look exactly like that, but plus -1, that's the same as minus +1. And I can see that answer up there. Our answer is A. All right, done. I'm happy with that. Celebrate. Next question. Have a try yourself. See how we go. All right, I really like questions like this because it feels kind of like there's not enough information. So it's a confidence interval question. We're going tech-free here. So let's pull up our formula. Here's our confidence interval. All right, so we're saying here that a confidence interval for the population mean is 91 to 99. So that means that this first part of the equation is 91, and this means the second part of this equation is 99. Now, if we find the middle of those two values, 91 and 99, we'll know what x bar is, right? Because x bar minus something and x bar plus something, if we know what two of those things are, we can look at the middle of them and know what x bar is. So, we know that x bar here is equal to 95. And we know that x bar minus z s over root n equals 91. Okay, we know that. The problem is that we don't know anything else. We know that's 95, sorry. We don't know anything else. We don't know what z is, we don't know what s is, and we don't know what root n is. But we know what the three of them grouped together is. We know that this is equal to 4. 95 minus 4 is equal to 91. The margin of error is 4. So z s over root n equals 4. So then the question becomes, if we increase n here by a factor of 16, so that it's not 16 anymore, get rid of that, so that it's not 16 anymore, it's 16n, what effect will that have on this, right? If we divide both, what we're essentially doing is dividing both sides by root 16. Divide that by root 16, divide that by root 16. Root 16 is 4. And 4 divided by 4 is 1. So what does that mean? Our margin of error, when we increase by a factor of 16, decreases by a factor of 4. Decreases by a factor of root 16. So, our mean's still the same, 95. But our margin of error is going to be 95 minus 1 and 95 plus 1. And I think I can see that value there. It is 94, 96. Cute question because it just feels like there's not enough there, but it's a question that comes up quite a bit, so keep an eye out for it. Celebration and on to the short response. All right, there's bound to be something like this on there. The plane exists such that it is perpendicular to this vector and contains the coordinates 1, 0, 4. Determine the Cartesian equation for the plane. All right, so let's find the Cartesian equation for the plane. We're just focusing on part A for now. All right, so an equation of a plane is r dot n equals a dot n. That's the vector equation of the plane. I like working with the vector equation of the plane. So r is just all the possible points, x, y, z, dot, and the vector that's normal says here that is perpendicular to this vector. 1, 1, 2. Now that's going to be equal to some point on the plane. I've got a point on the plane, 1, 0, 0. Dot product with something normal to the plane. Again, 1, 1, 2. Okay, we're aiming for the Cartesian equation. x dot 1, x plus y dot 1, y, z dot 2 plus 2z equals 1 dot 1, so that's 1, 0, 0, 0, just 1. All right, that's part A. I've found the Cartesian equation of the plane x plus y plus 2z equals 1. All right, give yourself a tick. Part B. Determine for what coordinates, if any, this plane has a point or line of concurrence with the following two planes. Boom, boom. We have 3 planes. We want to know where they meet, whether that's a line, a point, or not at all. If you're thinking about planes meeting at a point or at a line, you should be thinking about Gaussian elimination. All right, so these are our 3 planes. We've got to put them into an augmented matrix. Now, I'm going to choose, I can see the values, and you want to look a bit into the future. This plane that I've been asked to find in part A is a very simple, straightforward plane. In the way that I'm talking about it is a coefficient of 1, a coefficient of 1. This is going to be very useful as my first line of my augmented matrix. It's 1, 1, 2, 1. The next ones are 2, negative 1, 1, and 2, and 4, 1, 5, 4. 4, 1, 5, 4. Done. Now, there are all sorts of weird and wonderful ways to do Gaussian elimination, but here's what I advocate for, keeping it nice and simple and just kind of being a bit algorithmic about it, right? So, first thing I want to do is get rid of this and get rid of this, or more accurately, make this equal to 0 and make this equal to 0. And I do that by using row 1 in some way. All right, so, I need a thing there. All right, row 1 in this first step is not going to change at all. 1, 1, 2. All right, and then the question becomes, what multiple of row 1 do I need to add or subtract to row 2 to make this first element of row 2 0? All right, if I subtract 2 times row 1, I'll be in business. So the new row 2 is going to be equal to the old row 2 minus 2 times row 1. All right, think about how that notation looks. The new row 2, the row 2 that I'm about to create here, is equal to the original row 2 minus 2 times row 1. Okay, 2 minus 2 times that is 0. Negative 1 minus 2 times that is negative 3. 1 minus 4 is minus 3. And 2 minus 2 is 0. If I make one mistake, it's all over. I paused it, I double checked it, I'm feeling okay. Okay, next up, what multiple of row 1 do I need to add or subtract to row 2 to make 4 0? 4. So the new row 3 is going to be equal to the old row 3 minus 4 times row 1. Okay, 4 minus 4 is 0. 1 minus 4 is minus 3. And 5 minus 8 is minus 3. And 4 minus 4 is 0. Okay. Interesting. So it's certainly interesting, but let's proceed as planned, all right? We've got this 0 and this 0. The next algorithmic goal of our Gaussian elimination is to make this thing here equal to 0. So I'm going to do another thing up here. So this row isn't going to change, 1, 1, 2, 1. This second row isn't going to change, 0, negative 3, 0. But this row is going to change. And the question now is, what multiple of row 2 do we need to add or subtract to row 3 to make this element 0? If I subtract, and you need to be careful here, if I subtract negative 3 from negative 3, minus 3, minus 3, I'll get 0 there. Right, so my new row 3 is going to be equal to row 3 minus row 2. Okay, 0 minus 0, no surprises there, 0, it should always work that way. Negative 3 minus 3, 0. Negative 3 minus 3, 0. 0 minus 0, 0. Okay, interesting. A completely full row of zeros. 0, 0, 0, 0. You know what that means. I hope you do. we can say now, we can start sort of solving where these points meet, right? We can say 0z equals 0. Now that actually means that z can be anything. Z could be 2, right? Because 0 times 2 is equal to 0. Z could be 1,000,000. 0 times 1,000,000 is also equal to 0. So we can say now that we can set z to a parameter. We can say z is equal to lambda, just like that. Okay, so there's a good first step. Now, we sub this into our next line, and we can say that negative 3y minus 3 lambda is equal to 0. And we solve this for y. So we can say negative 3y plus 3 lambda, and then y is equal to 3 lambda divided by negative 3, which is negative lambda. All right, so z is equal to lambda, and y is equal to negative lambda. All right, our last one, we're going to sub in lambda and negative lambda for z and y into our first row. So 1x plus negative lambda plus 2 lambda equals 1. And we solve this for x. So we say x is equal to 1 plus lambda minus 2 lambda. So that's minus lambda. Okay. So I have 3 equations, or 3 variables now. I know z is equal to lambda, y is equal to negative lambda, and x is equal to 1 minus lambda. Rearranging these a little bit, I can say z is equal to lambda. I can say lambda is equal to negative y. And I can say lambda is equal to 1 minus x. So now I know that lambda is equal to z. Lambda is also equal to negative y, which means that z is equal to negative y. And I can also say that lambda is equal to 1 minus x. And z is equal to that, and negative y is equal to that, 1 minus x. So z equals negative y equals 1 minus x. So we're really finished here. What have we found? Determine for what coordinates, if any, plane 2 has a point or line of concurrence with the following 2 planes. So the way to answer this question is to say that the point of concurrence is this line. The 3 planes meet along that line. If you come across Gaussian elimination in a tech-free exam and you nail it, you should celebrate. Last question of the video. This question is a fun one. This is a good one. Have a try this. Alright, so I like this one. The reason I like this one is because you really should draw a picture. If you're not drawing pictures when you're dealing with questions like this, where they talk about complex numbers being on an Argand diagram, then you're kind of missing a trick. Okay, it says an equilateral triangle lies on an Argand diagram such that the vertices of the triangle are located at the origin. So there's one of the points. Then there is some other point, Z1. So let's just pick a random point for Z1. Let's put it, I don't know, here. Call that Z1. And then they say it's an equilateral triangle, right? So there's Z2. Alright, so there's my equilateral triangle. It could also not be that picture, right? It could be like origin, something there, and then 60-degree angle between the two. Right? I keep saying 60-degree angle because it's an equilateral triangle. Alright, so that might be Z1, that might be Z2. Or that might be Z1 and that might be Z2. But there's our basic understanding of what the question is. Now, in the question, it tells me to figure out or prove that Z1 cubed plus Z2 cubed is equal to 0. When I think of complex numbers being cubed, I think of them as being in polar form. Because cubing, raising a complex number to a power, is much easier when they're in polar form. So let's write these two in polar form, keeping in mind that we don't know anything about them. Alright, Z1 is equal to some magnitude, an unknown length. Just call it A. And then some angle measured from the x-axis. Now again, that angle might be a very small angle like that. It might be like a very large angle like that. It doesn't matter. But we can just say that angle, whatever that angle happens to be. Cis theta. Okay. Now, this other one, Z2, what can we say about that in complex number form? Well, we can say that it's got the same length because this is an equilateral triangle. Same magnitude, A. Cis. Now, we could just write it as A cis beta, right? And say that's that angle there. But by drawing this picture, hopefully you can see that this angle and this angle are related to each other, right? It's not cis beta, it's cis theta plus an extra 60 degrees. And again, this wouldn't matter where we were. If this was Z1 and this was Z2, theta plus 60 degrees. They're related to each other by that additional 60 degrees. This question practically solves itself now, I think. So we've got Z1, which is A cis theta. Or let's write it left-hand side, right-hand side. The left-hand side of our equation is Z1, which is A cis theta cubed plus Z2 cubed. So A cis theta plus 60 cubed. And the right-hand side of our equation is equal to 0. And we've got to prove that the left-hand side equals the right-hand side. Turn it around. Okay. A cis theta cubed, that's equal to A cubed cis and multiply the angle by 3. And this next one here is very similar. A cubed cis, and then we're multiplying this whole thing here by 3. So that's 3 theta plus 180. Okay, I don't need that extra bracket. Alright, so what do I see here? A cubed cis 3 theta. Now look at this interesting idea, right? 3 theta plus 180. What does that look like? What does it look like when you take a complex number? So 3 theta is just like some new angle, right? It's like, so it could, the complex number might look like this. But then when you add 180, you're just spinning it around. You just like that. Bam. That means that we can rewrite this complex number without the 180. Just by making it negative. A cubed cis 3 theta. Hopefully you're seeing how I'm getting from this line here to this line here. A rotation of 180 degrees is the same as multiplying a complex number by -1. Okay, we're done here, right? Because A cubed cis 3 theta minus A cubed cis 3 theta, they are the same thing. My answer is 0. The left-hand side equals the right-hand side. I don't know, QED, proven, whatever it is you want to write. However it is you celebrate when you prove something, celebrate. That's a good question. I love it. Short, sweet, but it really makes you think about drawing pictures when you work. Alright, that has been part 5 of Guessing the Specialist exam. As always, thanks to these people right here. Go and check them out. They're awesome. Alright, see you in the next one.